Group contain elements. Ful- uh, Fullerene, choline, bromine, iodine, astatine, and tennessine are the members of the group fontaine. These are collectively known as the halogens. Greek में halo means fault or gens means born. That means fault podophores. The halogens are highly reactive non-metallic elements like the group 1 and 2, and the elements of the group contain for the great similarity amongst themselves. That much similarity is not found in the elements of the other group of the periodic table. Also, there is a regular gradation in the physical and the chemical property. Astatine and the tennessine are the radioactive elements. Occurrence: Fluorine and the choline are fairly abundant while bromine and the iodine are less. So fluorine is present mainly as insoluble fluoride, fluorospark, CF2, chloride, Na3LF6 and fluoroapatite, Ca3, 4P2, CaF2, and a small quantity are present in soil, river water, plants and bones and the teeth of animals. Sea water contains chlorides, bromides and the iodides of the sodium, potassium, magnesium and calcium, but is mainly sodium chloride solution. 2.5% by mass. The deposit of a dried up fish contains these compounds: sodium chloride and the canalite, KCl, MgCl2 6H2O. Certain forms of the marine life contains iodine in their system. Various seaweeds, for example, contain up to 0.5% of the iodine, and a chill salt food contains up to 0.2% of the sodium iodate. Here, important atomic and the physical property of the group contain elements other than the tennessine are given along with their electronic configuration. Table 7.8, page 198. Tennessine is a synthetic radioactive element. Its symbol is TF, atomic number is 117, atomic number mass is 294, and the electronic configuration Rn 514, 6 7 F2, 7P5. Only very small amount of the element could be prepared. Also, its half-life in millisecond only, that is why its chemistry could not be established. यहाँ पर atomic and the physical property of halogens दिया हुआ है. Atomic number, atomic mass, electronic configuration, covalent radius, ionic radius, ionization enthalpy, electron gun enthalpy और melting point, boiling point, density, bond dissociation enthalpy, kilojoule per mole. The the trends The trends of the form of the atomic, physical, and the chemical property are discussed below. Electronic configuration. All these elements have 7 electrons in the red outermost shell, enough to NP5, which is 1 electron short of the next noble gas. Atomic and ionic radii. The halogens have the smallest atomic radii in the respective periods due to the maximum effective nuclear charge. The atomic radius of the fluorine, like the other atoms of the second period, is extremely small. Atomic and the ionic radii increase from the fluorine to the iodine due to the increasing number of the quantum shells. Ionization enthalpy. They have little tendency to lose electron, thus they have very high ionization enthalpy. Due to increase in the atomic size, ionization enthalpy decreases down the group. Electron gain enthalpy. Halogens have maximum negative electron gain enthalpy in the corresponding periods. This is due to the fact that the atoms of these elements have only 1 electron less than the stable noble gas configuration. Electron gain enthalpy of the elements of the group becomes less negative than the group. However, the negative electron enthalpy of the fluorine is less than that of the choline. It is due to the small size of the fluorine atom. As a result, there are strong inter-electronic repulsion in the relatively small 2p orbitals of the fluorine, and thus the incoming electron does not experience much attention. Now the electronegativity. They have very high electronegativity. The electronegativity decreases down the group. Fluorine is the most electronegative element in this periodic table. Halogens have maximum negative electron gun enthalpy in the respective periods of the periodic table Y. So halogens have the smallest charge in their respective periods and therefore high effective nuclear charge. As a consequence, they rarely accept 1 electron to acquire noble gas electronic configuration. Physical properties. Halogen display a smooth variation in their physical properties. Fluorine and choline are gases, bromine is a liquid, and iodine is a solid. Their melting and the boiling points steadily increase with atomic number. All halogens are colored. This is due to the absorption of the radiation in the visual region, which results in the excitation of the outer electrons to a higher energy level. By absorbing different quanta of the radiation, they display different colors. For example, F2 has yellow, Cl2 greenish yellow, Br2 red, and the I2 violet color. Fluorine and the choline react with water. Bromine and iodine are only strongly soluble in the water, but are soluble in the various organic solvents such as the chloroform, carbon tetrachloride, carbon disulfide, and the hydrocarbons to give the colored solution. One curious anomaly we notice from the table 7.8 is that a smaller enthalpy of the diffusion of the F2 compared to that of the Cl2, whereas XX bond diffusion enthalpy from the chlorine onward for the expected trends Cl2, Br2, I2. A reason for this anomaly is the relatively larger electron repulsion among the lone pairs of in the F2 molecule, where they are much closer to each other than in the case of the Cl2. Examples 1.15. All low electron gain enthalpy of the fluorine is negative as compared to the coldene. Fluorine is a stronger oxidizing agent than the coldene. Why? It is due to the low enthalpy of the dissociation of the FF bond, high hydrogen enthalpy of the F minus. Now the chemical properties. Oxidation states and the trends in the chemical reactivity. All the halogen exhibits -1 oxidation state. However, coldene, bromine, and the iodine exhibits +1, +3, +5, and +7 oxidation state also, as explained below. Halogen atom in the ground state other than the fluorine, first excited state, second excited state, and the third excited state. +1 unpaired electron accounts for the -1 and +1 oxidation state. +3 unpaired electrons account for the +3 oxidation state. +5 unpaired electron accounts for the +5 oxidation state. 7 unpaired electron accounts for the +7 oxidation state. Now the higher oxidation states of the coldene, bromine, iodine are realized mainly when the halogens are in combustion with the small and the highly electronegative fluorine and oxygen atoms. Example in the interhalogens, oxides, and the oxoacids. The oxidation states of +4 and +6 occur in the oxides and oxoacids of the coldene and the bromine. The fluorine atom has no d orbitals and is valence shell and therefore cannot expand its octet. Being the most electronegative, it exudes only -1 oxidation state. All the halogens are highly reactive. They react with the metals and non-metals to form the halides. The reactivity of the halogens decreases down the group. The ready acceptance of the electron in the region for the strong oxidizing nature of the halogens. F2 is the strongest oxidizing halogen and it oxidizes further halide ions in the solution or even in the solid phase. In general, a halogen oxidizes halide ions of the higher atomic number. जैसे F2 +2x माइनस F1 माइनस, जहाँ पर x2 जो है एक्स कोलिन, ब्रोमीन और आयोडीन हो सकता है. फिर Cl2 +2x माइनस, तो 2Cl माइनस प्लस x2 जहाँ पर ब्रोमीन और आयोडीन होगा. और फिर Br2 +2I माइनस Br माइनस प्लस I2 हो जाएगा. ये इसका रिएक्शन होता है. The decreasing oxidizing ability of the halogens in the aqueous solution down the group is evident from the standard electrode potentials, which are evident on the parameter indicated below. हाफ x2 हाफ डिसोसिएशन इंथैल्पी x और उसमें से इलेक्ट्रॉन की इंथैल्पी फिर तो किए तो x माइनस और x माइनस में हीट ऑफ हाइड्रेशन दिए तो x माइनस एक्वस बन गया, गैसियस एक्वस. द रिलेटिव स्टेबिलिटीज. The relative oxidizing power of the halogen can further be illustrated by the reaction with the water. Fluorine oxidize water to oxygen, whereas choline and the bromine react with the water to form corresponding hydrohalic and the hypohalous acid. The reaction of the iodine with the water is non-spontaneous. In fact, I minus can be oxidized by the oxygen in the acidic medium, just the reverse of the reaction observed with the fluorine. जैसे F2 प्लस H2O H प्लस F माइनस प्लस O2 देगा और फिर X2 प्लस H2O HX प्लस HOX देगा, जहाँ X बराबर कोलिन और द ब्रोमीन है. फिर I माइनस प्लस H प्लस प्लस O2 I2 प्लस H2O देगा. Now the anomalous behavior of the fluorine. Like other elements of the p block present in the second period of the periodic table, fluorine is anomalous in many properties. For example, ionization, enthalpy, electronegativity, and electrode potential are all higher for the fluorine than expected from the trend set by the other halogen. Also, ionic and the covalent radii, melting point and the boiling point enthalpy of bond dissociation and electron gain enthalpy are quite lower than the expected. The anomalous behavior of the fluorine is due to small size, high electronegativity, low fluorine bond dissociation enthalpy, and non-availability of the d orbitals in the valence shell. Most of the reactions of the fluorine are exothermic due to the small and the strong bond formed by it with the help of the elements. It forms only one oxoacid, while other halogens forms a number of the oxoacid. Hydrogen fluoride is a liquid, boiling point 293 Kelvin due to the strong hydrogen bonding. Hydrogen bond is formed in the HF due to the small size and the high electronegativity of the fluorine. Other hydrogen halides which have bigger size and less electronegativity are the gases. Now the reactivity towards the hydrogen. They all react with the hydrogen to give the hydrogen halide, but for affinity for the hydrogen decreases from the fluorine to the iodine. Hydrogen halide dissolve in the water to form a hydrohalic acid. Some of the properties of the hydrogen halides are given in the table 7.9. The acidic strength of the acid varies in the order of subsadi Hi, usakam HBr, usakam HCl, or subsakam HF. The stability of these halides decreases down the group due to the decrease in the bond HF dissociation enthalpy in the order of HF, फिर उससे कम HCl, उससे कम HBr और सबसे कम HI. तो मेल्टिंग पॉइंट दिया हुआ है, बॉइलिंग पॉइंट, बॉन्ड लेंथ और डिसोसिएशन एंथैल्पी किलोजूल पर मोल में, और pKa वैल्यू दिया हुआ है HF का, HCl का, HBr का और द HI का. फिर आता है reactivity towards the oxygen. Halogen form many oxides with oxygen, but most of them are unstable. Fluorine forms two oxides, OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluoride because of their higher electronegativity of the fluorine than the oxygen. Both are strong fluoridating agents. O2F2 oxidize plutonium to PuF6, and the reaction is used in the removing plutonium as PuF6 from the spent nuclear fuel. Chlorine, bromine, and iodine form oxides in which the oxidation state of these halogen range from +1 to +7. A combination of the kinetic and the thermodynamic factors lead to the generally decreasing order of the stability of the oxides formed by the halogen. I, second fuel Br, higher stability of the oxides of the iodine is due to the greater polarizability of the bond between the iodine and the oxygen. In the case of the chlorine, multiple bond formation between the chlorine and the oxygen take place due to the ability of the d orbitals. This leads to the decrease in the stability. Bromine lacks both the characteristic, hence the stability of the oxides of the bromine is left. The higher oxides of the halogen tend to be more stable than the lower ones. Chlorine oxide, Cl2O, ClO2, and the Cl2O6 and the Cl2O7 are highly reactive oxidizing agents and tend to explode. ClO2 is used as a bleaching agent for paper pulp and the textile and in the water treatment. The bromine oxides Br2O, BrO2, and the BrO3 are the least stable halogen oxides, middle row anomaly, and used only at low temperature. They are very powerful oxidizing agents. The iodine oxides I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in the estimation of the carbon monoxide. Reactivity towards metal. Halogen reacts with the metals to form metal halides. For example, bromine reacts with the magnesium to give magnesium bromide. Mg plus Br2, MgBr2. The ionic character of the halides decrease in the order Mf, Mcl, Mbr, Mi, where M is a monovalent metal. If the metal exhibits more than one oxidation state, the halides in the higher oxidation state will be more covalent than the one in the lower oxidation state. For example, FnCl4, PbCl4, FbCl5, and the UF6 are more covalent than the FnCl2, PbCl2, FbCl3, and the UF4 respectively. Reactivity of the halogen towards the other halogen. Halogens combine amongst themselves to form a number of the compounds known as interhalogens of the type XX-, XX3-, XX5-, and XX7-, where X is a larger size halogen and X is a smaller size halogen. Example 7.16, fluorine exhibits +1 or -1 oxidation state, whereas other halogens exhibit +3, +5, +7, and +1, +3, +5, and +1 oxidation state also. Explain. The fluorine is the most electronegative element and cannot exhibit any positive oxidation state. Other halogens have d orbitals and therefore can expand their octet and 4 +3, +5, +7 oxidation state also. Now the in-text question. Considering the parameters such as the bond diffusion enthalpy, electron gain enthalpy, and the hydrogen enthalpy, compare the oxidizing power of the F2 and the Cl2. Give two examples to show the anomalous behavior of the fluorine, or C is the greatest source of some halogen. Comment. Now the chlorine. Chlorine was discovered in the 2024 by the Skilly by the action of the HCl on the MnO2. In 1810, Davy established its elementary nature and suggests that name chlorine on account of its color, Greek chloros, greenish yellow. Preparation. It can be prepared by any one of the following method: by heating manganese dioxide with the concentrated hydrochloric acid, जैसे MnO2 प्लस HCl को गर्म किएंगे तो MnCl2 प्लस Cl2 प्लस H2O मिलेगा. However, the mixture of the common salt and the concentrated A2SO4 is used in the place of the HCl. जैसे NaCl plus MnO2 plus H2SO4 MnCl2 plus NaHFO4 plus H2O plus Cl2 मिलेगा। उसके बाद फिर आता है कि बाय द एक्शन ऑफ द HCl ऑन द पोटेशियम पर मैग्नेट, जैसे KMnO4 plus KMnO4 plus H16HCl KCl plus KMnO4 plus HCl KCl plus MnCl2 plus H2O plus Cl2 मिल जाएगा। Now the manufacture of the choline decomposes by the oxidation of the hydrogen chloride gas by the atmospheric oxygen in the presence of the FeCl2 catalyst at the 723 Kelvin. HCl plus O2 FeCl2 Cl2 plus H2O बना देगा। Now the electrolytic process, choline is obtained by the electrolysis of the brine concentrated in a solution. Choline is liberated at anode. It is also prepared by a byproduct in many chemical industries. Properties: it is a greenish yellow gas with pungent and suffocating odor. It is about 2 to 5 times heavier than the air. It can be liquefied easily into the greenish yellow liquid which boils at 239 Kelvin. It is soluble in the water. Choline reacts with a number of the metals and non-metals to form the chlorides, जैसे Al plus Cl2 LCl3 Na plus Cl2 NaCl and the Fe plus Cl2 FeCl3, फिर P4 plus Cl2 PCl3 and the F8 plus Cl2 F2Cl2. It has great affinity for the hydrogen. It reacts with the compounds containing hydrogen to form the HCl, जैसे H2 plus Cl2 HCl, H2S plus Cl2 HCl plus S और the C10 H16 plus Cl2 HCl plus 10CO, ये बन जाता है। उसके बाद फिर आता है कि with cold and dilute alkalis, choline produces a mixture of the chloride and the hypochlorite, but with the hot and the concentrated alkalis, it gives the chloride and the chlorate. NaOH plus Cl2, NaCl plus NaCl plus H2O, NaOH plus Cl2, NaCl plus NaCl plus H2O, then the NaOH plus NaOH plus Cl2, NaCl plus NCl3 plus H2O. With dry flake lime, it gives bleaching powder CaOH2 plus Cl2, CaOCl2 plus CaCl2 plus H2O. The composition of the bleaching powder is CaOCl2 plus CaCl2 plus CaOH2 plus into 2H2O. The composition of the bleaching powder is CaOCl2 dot CaCl2 dot CaOH2 dot 2H2O. Choline reacts with the hydrocarbons and gives substitution products with saturated hydrocarbons and addition products with the unsaturated hydrocarbons. For example, CH4 methane जो कि है plus Cl2 gives the CH3Cl methyl chloride plus HCl, और फिर इथाइन C2H4 plus Cl2 रूम टेम्परेचर पर C2H4 Cl2 1,2 डाइक्लोरो इथेन दे देगा। अब आता है कि choline water on standing loses its color due to the formation of the HCl and the HOCl. Hypochlorous acid HOCl is formed, gives nascent oxygen which is responsible for oxidizing and bleaching property of the choline. Now the choline oxidizes ferrous to ferric and the sulfide to sulfate. Choline oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In the presence of the water, they form sulfuric acid and iodic acid respectively. FeSO4 plus H2SO4 plus Cl2 Fe2SO4 के 3 plus HCl, Na2SO3 plus Cl2 H plus H2O, Na2SO4 plus HCl, FO2 plus H2O plus Cl2 H2SO4 plus HCl, I2 plus H2O plus Cl2 HiO3 plus H10H मतलब HCl बना देगा। Choline is a powerful bleaching agent. Bleaching action is due to the oxidation. It bleaches vegetable or the organic matter in the presence of the moisture. Bleaching effect of the choline is permanent. Cl2 plus H2O to HCl plus O बना देगा। Colored substance plus O colorless substance दे देगा। Now the usage, it is used for bleaching wood pulp required for the manufacture of the paper and the rayon, bleaching cotton and the textile, in the extraction of the gold and the platinum, in the manufacture of the dye, drugs and organic compounds such as the CCl4, CCl3, DDT, refrigerants, etc., in sterilizing drinking water and the preparation of the poisonous gases such as the phosgene, tear gas, CCl3, NO2, mustard gas, Cl, CH2, CH2S, CH2, CH2Cl. Example 7.17 है कि write the balanced chemical equation for the reaction of the Cl2 with the hot and the concentrated NaOH. In this reaction, a disproportionation reaction. Is this reaction a disproportionation reaction? Justify. The Cl2 plus NaOH NaCl plus NClO3 plus H2O, ये रिएक्शन हो गया. और फिर इन क्लोरीन फॉर्म 0 ऑक्सीडेशन स्टेट चेंज टू -1 एंड +5 ऑक्सीडेशन स्टेट, इसलिए डिस्प्रोपोर्शनेशन है. फिर इन टेक्स्ट क्वेश्चन गिव द रीजन फॉर द ब्लीचिंग एक्शन ऑफ द Cl2, नेम 2 पॉइजनस गैस विच कैन बी प्रिपेयर्ड फ्रॉम द क्लोरीन गैस. हाइड्रोजन क्लोराइड. Glauber prepared this acid in the 5048 by heating common salts with the concentrated sulfuric acid, Davy in the 1810, so that it is a compound of the hydrogen and the chlorine. Preparation in the laboratory, it is prepared by heating sodium chloride with the concentrated sulfuric acid, NaCl plus H2SO4 at 420 Kelvin per give the NaHFO4 plus HCl, और फिर NaHFO4 plus NaCl at 27 Kelvin per give the Na2SO4 plus the HCl. HCl gas can be dried by passing through the concentrated sulfuric acid. Properties ki it is a colorless and the pungent smelling gas. It is easily liquefied to a colorless liquid, boiling point 180 Kelvin, and freezing to a white crystalline solid, freezing point 159 Kelvin. It is extremely soluble in the water and ionized as follow. HCl plus H2O H2O plus Cl minus देगा, जिसका Ka वैल्यू है 8×10⁻⁷. Its aqueous solution is called hydrochloric acid. High value of the dissociation constant Ka indicates that it is a strong acid in the water. It reacts with NH3 and gives the white form of the NH4Cl. NH3 plus HCl देगा NH4Cl. Now when 3 parts of the concentrated HCl and 1 part of the concentrated HNO3 are mixed with aqua regia is formed, which is used for the dissolving noble metals जैसे gold, platinum etc. अब इसका रिएक्शन है कि Au प्लस 4H प्लस NO3 माइनस प्लस 4HCl माइनस AuCl4 माइनस प्लस NO प्लस H2O और 3Pt प्लस 16H प्लस 4 NO3 प्लस Cl माइनस PtCl6 माइनस प्लस NO प्लस H2O देगा. अब आता है कि हाइड्रोक्लोरिक एसिड डिकम्पोज साल्ट्स. हाइड्रोक्लोरिक एसिड डिकम्पोज साल्ट्स ऑफ द बिकर एसिड जैसे कि कार्बोनेट्स, हाइड्रोजन कार्बोनेट, सल्फाइड्स एक्सेट्रा. Na2CO3 प्लस HCl NaCl प्लस H2O प्लस CO2. उसके बाद फिर NaHCO3 प्लस HCl NaCl प्लस H2O प्लस CO2, Na2SO3 प्लस HCl NaCl प्लस H2O प्लस SO2 दे देगा. उसके बाद फिर आता है यूजेज. It is used in the manufacture of the chlorine, NH4Cl and glucose from the corn starch for extracting glue from the bones and the purifying bone blacks, in medicine and as a laboratory reagent. Examples 1.18. When HCl reacts with finely powdered iron, it forms ferrous chloride and not ferric chloride. Bhai, it reaction with the iron produces H2 Fe plus HCl FeCl2 plus H2. Liberation of the hydrogen prevents the formation of the ferric chloride. Now the oxo acids of the halogen. Oxo acids of the halogen. Now the oxo acids of the halogen, due to high electronegativity and the small size, fluorine forms only one oxo acid HOF, known as the fluoric 1 acid or the hypofluorous acid. The other halogens forms several oxo acids. Most of them cannot be acylated in the pure state. They are stable only in the aqueous solution or in the form of their salts. The oxo acids of the halogen are given in table 1.1 and their structure are given in the figure 1.8. तो इधर दिया हुआ है हैलिक एसिड, फिर हैलिक 3 एसिड, हैलिक 5 एसिड एंड हैलिक 1 एसिड. HOF हाइपोफ्लोरस एसिड, HOCl हाइपोक्लोरस एसिड, HOBr हाइपोब्रोमस एसिड एंड HOI हाइपोआयोडस एसिड. तो इधर HOClO यानी क्लोरस एसिड, HOClO2 क्लोरिक एसिड, HOClO3 पर क्लोरिक एसिड. फिर HOBrO2 ब्रोमिक एसिड, HOBrO3 पर ब्रोमिक एसिड, HOIO2 आयोडिक एसिड, HOIO3 पर आयोडिक एसिड. अब स्ट्रक्चर दिया हुआ है हाइपोक्लोरस एसिड का, फिर हो गया क्लोरस एसिड, फिर क्लोरिक एसिड और फिर पर क्लोरिक एसिड. द स्ट्रक्चर ऑफ द ऑक्सो एसिड्स ऑफ द क्लोरीन. Interhalogen compounds. When the two different halogens react with each other, interhalogen compounds are formed. They can be assigned general composition as XF dash, XF3 dash, XF5 dash, XF7 dash, where X is the halogen of larger size and X dash of the smaller size, and X is more electropositive than the X. As the ratio between the radii of the X and the X dash increases, the number of the atoms per molecule also increases. Thus, the iodine 7 fluoride should have maximum number of the atoms as the ratio of the radii between the one I and the F should maximum. That is why its formula is IF7 having the maximum number of the atoms. Preparation. The interhalogen compounds can be prepared by the direct combination or by the action of the halogen or the lower interhalogen compounds. The product format depends upon the some specific condition, जैसे Cl2 plus F2 to ClF, Cl2 plus F2 ClF3 और the I2 plus Cl2 इकोमोलर जो दे देगा हमको ICl. उसके बाद फिर I2 plus Cl2 ICl3 Br2 plus F2 BrF3 Br2 plus 5F2 एक्सेस में BrF5 दे देगा. फिर आता है some properties of the interhalogen compounds are given in table 7.1. Some properties of the interhalogen compounds X dash जिसका ClF जो XF dash 1 में ClF BrF IF3 BrCl5 ICl आता है और ClF जो है वो है ClF ब्राउन गैस है BrF पेल ब्राउन गैस है IF5 डिटेक्टेड स्पेक्ट्रोस्कोपिकली BrCl5 गैस है ICl रूबी रेड सॉलिड अल्फा फॉर्म ब्राउन रेड सॉलिड बीटा फॉर्म और IBr ब्लैक सॉलिड है. फिर ClF3 कलरलेस गैस है ClF3 कलरलेस गैस है BrF3 येलो ग्रीन लिक्विड है IF3 येलो पाउडर है ICl ऑरेंज सॉलिड है. IF कलरलेस गैस है बट सॉलिड बिलो 77 केल्विन पर. BrF5 कलरलेस लिक्विड है ClF5 कलरलेस लिक्विड है IF7 कलरलेस गैस है. उसके बाद फिर आता है कि ClF3 बेंट टी शेप है BrF3 IF3 ICl3 सब के सब बेंट टी शेप है ये सब. उसके बाद फिर आता है IF5 स्क्वायर पिरामिडल है BrF5 स्क्वायर पिरामिडल है ClF5 स्क्वायर पिरामिडल है. फिर IF7 जो है वो पेंटागोनल पिरामिडल है. These are all covalent molecules and are dimagnetic in nature. They are volatile solids or liquid at 298 Kelvin except ClF, which is a gas. The physical properties are the intermediate between those of the constituent halogen except that at their melting point and boiling point and are a little higher than the expected. Their chemical reaction can be compared with the individual halogens. In general, interhalogen compounds are more reactive than the halogen except fluorine. This is because of the excess bond in the interhalogen is bigger than the excess bond in the halogens except FF bond. All these undergo hydrolysis giving halide and derived from the smaller halogen and is a hypohalite when excess dash, halite when the excess 3 dash and the halate when excess 5 dash and per halate excess 7 dash anion derived from the larger anion. Excess dash plus H2O gives the HX plus HOX. The intermolecular structure are very interesting, which can be explained on the basis of the BSEPR theory. The XF3 compounds have the bent T-shape, XF5 compound a square pyramidal, and IF7 has the pentagonal bipyramidal structure. Now the example. Discuss the molecular shape of the BrF3 on the basis of the BSEPR theory. The central atom of the Br has 7 electrons in the valence shell. 3 of these will form the electrons pair bond with the 3 fluorine atoms, leaving behind 4 electrons. Thus, there are 3 bond pairs and 2 lone pairs. According to BSEPR theory, these will occupy the corners of a trigonal bipyramid. The 2 lone pair will occupy the equatorial position to minimize lone pair, and thus the bond pair lone pair repulsion, which are greater than the bond pair repulsion. In addition, the axial fluorine atoms will be bent towards the equatorial fluorine in order to minimize the lone pair for repulsion. Thus the shape would be slightly bent T. उसके बाद फिर आता है कि इसका यूजेज क्या है. तो these compounds can be used as a non-aqueous solvents. Interhalogen compounds are very useful phonetic agents. ClF3 and the BrF3 are used for the production of the UF6 and the enrichment of the U35. फिर इसका U plus ClF3 UF6 plus ClF दे देगा. फिर आता है कि why ICl more reactive than the I2. in text question. Now the group 18 elements. Group 18 consists of the elements helium, neon, argon, krypton, xenon, radon, and the organophone. All they are gaseous and chemically unreactive. They form very few compounds. Because of this, they are termed as the noble gases. Occurrence: all these gases except radon and the organophone occur in the atmosphere. The atmospheric abundance in the dry air is about 1% by the volume of which argon is the major constituent. Helium and sometimes neon are found in the minerals of the radioactive origin, that means pitchblende, monazite, cleveite. The main commercial source of the helium is natural gas. Xenon and the radon are the rarest elements of the group. Radon is obtained as a decay product of the रेडियम 226 और फिर रेडियम 226 को डिके करेंगे तो रेडॉन और 4 मतलब हीलियम मिलेगा, तो ये इसका हो जाता है. उसके बाद फिर ऑर्गेनाइजेशन हैज बीन सिंथेटिकली प्रोड्यूस्ड बाय द कोलिजन ऑफ द CF249 एटम्स एंड द Ca48 आयंस. तो CF249 को Ca48 से करेंगे तो ऑर्गेनाइजेशन प्लस 3 न्यूट्रॉन मिलेगा. Why are the elements of the group 18 known as the noble gases? The elements present in the group 18 have their valence shell orbital completely filled and therefore react with a few elements only under the certain condition. Therefore, they are known as the noble gases. Organization has its symbol Og, atomic number 118, atomic mass 249, and the electronic configuration Rn 5f14 6d10 1f2 7p6. Only very small amount of the Og has been produced. Its half-life is 0.7 millisecond. Therefore, many predictions about its chemistry have been made. Here, except for the organization, important atomic and the physical property of the other elements of the group 18 along with their electronic configurations are given in table 1.12. The trends in some of the atomic, physical, and the chemical property of the group are discussed. जैसे कि एटॉमिक नंबर, एटॉमिक मास, इलेक्ट्रॉनिक कन्फिगरेशन, एटॉमिक रेडियस, आयोनाइजेशन एंथैल्पी, इलेक्ट्रॉन गेन एंथैल्पी, डेंसिटी, मेल्टिंग पॉइंट, बॉइलिंग पॉइंट एंड द एटमॉस्फेरिक कंटेंट बाय द वॉल्यूम. तो हीलियम, नियन, आर्गन, क्रिप्टॉन, जीनॉन एंड द रेडॉन. Electronic configuration. All noble gases have general electronic configuration NF2np6 except helium, which has 1f2. Many of the properties of the noble gas, including their inactive nature, are ascribed to the closed shell structure. Ionization enthalpy. Due to the stable electronic configuration, these gases used very high ionization enthalpy. However, it decreases down the group with increase in the atomic size. Atomic radii increases down the group with the increase in the atomic number. Since the noble gas have the stable electronic configuration, they have no tendency to accept electrons and therefore have large value of electron gain enthalpy. Physical properties. All the noble gases are monoatomic. They are colorless, odorless, and tasteless. They are strongly soluble in the water. They have very low melting and the boiling points because the only type of the interatomic interaction in these elements is a weak dispersion force. Helium has the lowest boiling point, 4.2 Kelvin of any known substance. It has an unusual property of diffusing through the most commonly used laboratory materials such as the rubber, glass और the plastics. और शायद इसको है जो 2023 में पूछा था शायद. Noble gases example 7.21. Noble gases have very low boiling point. Why? So noble gases being monatomic have no interatomic forces except weak dispersion forces and therefore they have liquefied at a very low temperature, hence they have low boiling points. Now the chemical properties. In general, noble gases are least reactive. Their inertness to the chemical reactivity is attributed to the following reasons. The noble gas except helium have completely filled NF2np6 electronic configuration in their valence shell. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of the noble gas has been investigated occasionally ever since their discovery, but all the attempts to force them to react to form the compounds were unsuccessful for quite a few years. In March 1962, Neil Bartlett, then at the University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2PtF6-. He then realized that the first ionization enthalpy of the molecular oxygen 1175 kJ per mole was almost identical with that of the xenon 1170 kJ per mole. He made efforts to prepare some type of the compounds with xenon and was successful in preparing another red color compound XePtF6- by mixing PtF6 and the xenon. After this discovery, a number of the xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. The compounds of the krypton are fewer. Only the difluoride KrF2 has been studied in detail. Compounds of the radon have not been isolated. but only identified RNF2 by the radio-transfer technique. No true compounds of the ARNE or the HE are yet known. A. Xenon fluoride compounds. Xenon forms three binary compounds XCF2, XCF4 and the XCF6 by the direct reaction of elements under appropriate experimental condition. Xc plus F2 Xc plus F2 673 केल्विन एक बार पर XcF2 देगा, फिर Xc+2F2 XcF4 देगा और Xc+3F2 एक ई था एक जिनॉन इन द एक्सेस में, यह 1:5 रेशियो में, यह 1:20 रेशियो में जो देगा XcF6 देगा. तो जिनॉन XcF6 can also be prepared by the interaction of XcF4 and O2F2 at the 143 Kelvin. जैसे XcF4 plus O2F2 XcF6 plus O2 देगा at 143 Kelvin per. XcF2, XcF4 and XcF6 are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They are readily fertilized even by the trappage of the water. For example, XcF2 is fertilized to give the XcHF and the O2. XcF2 plus H2O, XcF2 plus H2O give the Xc plus 4HF plus O2. ये इसका रिएक्शन हो गया. फिर the structure of the three xenon fluorides can be derived from the BSEPR, and these are shown in the figure 1.9. XcF2 and XcF4 have linear and square planar structure respectively. XcF6 has 7 electron pairs, 6 bonding and the 1 lone pair, and would thus have distorted octahedral structure and found experimentally in the gas phase. Xenon fluorides react with the fluoride ion acceptors to form the cationic species and fluoride ion donors to form the fluoroanions. XcF2 plus PF5, XcF plus PF6 minus, or XcF4 plus SbF5, XcF3 plus SbF6 minus, or XcF6 plus MF, M plus XcF7 minus, M बराबर Na K Rb और दी CF हो जाता है. अब फिर उसके बाद फिर आता है जिनॉन oxygen compounds. Hydrolysis of the XcF4, hydrolysis of the XcF4 and the XcF6 with the water gives the XcO3. XcF4 plus H2O gives the Xc plus XcO3 plus HF plus O2, and XcF6 plus H2O gives the XcO3 plus HF. Partial hydrolysis of XcF6 gives the oxyfluoride XcOF4 and the XcO2F2. XcF6 plus H2O gives the XcOF4 plus HF, or XcF6 plus H2O gives the XcO2F2 plus HF. अब आता है कि यह है लीनियर स्ट्रक्चर हो गया, और स्ट्रक्चर ऑफ द XcF2 हो गया, ये हो गया XcF4 स्क्वायर प्लेनर, फिर X6 डिस्टॉर्टेड ऑक्टाहेड्रल, और XcOF4 स्क्वायर पिरामिडल, और फिर XcO3 पिरामिडल हो गया. XcF6 प्लस H2 XcOF4 प्लस 2HF है, और XcF प्लस H2 होगी XcO2F2 है. तो ये इंपॉर्टेंट रिएक्शंस हो गया. फिर एक इम्पॉर्टेंट रिएक्शन से हो गया नाउ दी XcO3 is a colorless explosive solid and has a pyramidal molecular structure. XcO4 is a colorless volatile liquid and has a square pyramidal molecular structure. Question 1 है कि does the hydrolysis of XcF6 lead to a redox reaction? No, the products of the hydrolysis of the XcO4, XcOF4 and XcO2F2 bear the oxidation states of the elements remain the same as it was in the reacting state. Uses कि helium is a non-inflammable and light gas and it is used in the filling balloons for the meteorological observation. It is also used in the gas-cooled nuclear reactor. Liquid helium boiling point 4.2 Kelvin find used as a cryogenic agent for carrying out powerful various experiments at low temperature. It is used to produce and sustain powerful superconducting magnets, which forms an essential part of the modern NMR spectrometers and magnetic resonance imaging system for the clinical diagnosis. It is used in the dilute for the oxygen in the modern diving apparatus because of its low solubility in the blood. Neon is used in discharge tubes and fluorescent bulbs for advertisement display purpose. Neon bulbs are used in the botanical gardens and in the greenhouses. Argon is used mainly to provide an inert atmosphere in the high temperature metallurgical processes, arc building of the metals for the alloy, and for filling electric bulbs. It is also used in the laboratory for handling the substances that are air sensitive. There are no significant use of the xenon and the krypton. They are used in the light bulbs designed for the special purpose. In text question, why is helium used in the driving apparatus? Balance the following equation: XCF6 plus H2O, XO2, F2 plus HF. Why it has been difficult to study the chemistry of the radon? Now the summary. Group 13 to 18 of the periodic table consists of the p block elements with their valence shell electronic configuration NF to NP1 to 6. Group 13 and the 14 were dealt in class 11. In this unit, remaining group of the p block have been discussed. Group 15 consists of the 5 element family nitrogen, phosphorus, arsenic, antimony, and the bismuth, which have general electronic configuration NF to NP3. Nitrogen differs from other elements of this group due to the small size formation of the p-pi multiple bonds with itself and with the high electronegative atoms like the oxygen or the carbon, and non-ability of the d orbitals to expand its valence shell. Elements of the group 15 show gradation in the property. They react with the oxygen, hydrogen, and the halogens. They exhibit two important oxidation state, +3 and the +5, but +3 oxidation is favored by the heavier elements due to the inert pair effect. Dinitrogen can be prepared in the laboratory as well as on the industrial scale. It forms oxides in a various oxidation state as the N2O, NO, N2O3, NO2, N2O4, and the N2O5. These oxides have resonating structure and have multiple bonds. Ammonia can be prepared on a large scale by the Haber process. HNO3 is an important industrial prepared on a large scale by the HNO3 is an important industrial chemical. It is a strong monobasic acid and is a powerful oxidizing agent. Metals and non-metals react with the HNO3 under different conditions to give the NO or the NO2. Phosphorus is used as the P4 in the elemental form. It is used in the several allotropic forms. It forms hydride PH3, which is a highly poisonous gas. It forms two types of halides, either PX3 and the PX5. PCl3 is prepared by the reaction of the white phosphorus with dry chlorine, while the PCl5 is prepared by the reaction of phosphorus with the FO2Cl2. Phosphorus forms a number of the oxoacids depending upon the number of the pH group. Their viscosity varies. The oxoacids which have pH bonds are good reducing agents. The group 16 elements have general electronic configuration of 24. Therefore, maximum oxidation state +6. Gradation in the physical and the chemical property is observed in the group 16 elements. In the laboratory, dioxide is prepared by heating KCl3 in the presence of the MnO2. It forms a number of the oxides with the metals. KCl2 is in presence of NO3. It forms a number of oxides with the metals. Allotropic form for the oxygen is O3, which is a highly oxidizing agent. Sulfur forms a number of the allotropes. Of these, alpha and beta form for the sulfur are the most important. Sulfur combines with the oxygen to give the oxides such as FO2, FO3. FO2 is prepared by the direct union of the sulfur with the oxygen. FO2 is used in the manufacture of the H2SO4. Sulfur forms a number of the oxo acids. Amongst them, the most important is the H2SO4. It is prepared by the contact process. It is dehydrating and oxidizing agent. It is used in the manufacture of the several compounds. Now the group 17 of the periodic table consists of the fluorine, chlorine, bromine, and the iodine and the astatine. All these elements are extremely reactive, and as such they are found in the combined state only. The common oxidation state of these is the -1. However, highest oxidation state can be +7. Therefore, regular gradation in the physical and the chemical properties. They form oxides, hydrogen halides, interhalogen compounds, and the oxo acids. Chlorine is conventionally obtained by the reaction of HCl with the KMnO4. HCl is prepared by the heating NaCl with the concentrated HCl4. Halogens combines with the one another to form the interhalogen compounds. One type of XN 1357, where X dash is lighter than the X. A number of oxoacids of the halogens are known in the structure. These oxoacid halogen is a central atom which is bonded in each case with one OH bond. XOH, in some cases XO bonds are also found. Group 18 of the periodic table consists of the noble gas. They have NF2 NP6 valence small shell electronic configuration except helium, which has 1f2. All the gases except radon occur in the atmosphere. Radon is obtained as a decay product of the 226 radium. Due to the complete octet of the outermost shell, they have less tendency to form the compounds. The best characterized compound are those of xenon with fluorine and chlorine oxygen under the certain condition. These gases have several uses. Argon is used to provide inert atmosphere. Helium is used in the filling balloons for the meteorological observation, and neon is used in the discharge tubes and the fluorescent bulbs.